Good morning. Can you hear me?
Good morning, sir. Yes, you can. So I guess your mic is still mute.
Okay. All right. Everything is audible now?
Yes, it is.
Okay. I think in the last lecture, we finally concluded uh, by actually deriving an expression for the rate at which uh, gas moves from the gas phase um, to the liquid phase. And um, um, basically, we started off with a very general model in the last lecture, reduced that from a very, very complicated model to a simple model involving only two films or boundary layers on either side of the gas liquid boundary, that is to say, the boundary between the bubble and the liquid. And this was the original picture we started off with under a series of assumptions that the concentration of the gas in the bulk phase, which is expressed in partial pressure, right? Partial pressure is a reasonable measure of concentration uh, because, I mean, I'll just put it down here since I've not mentioned it and one never knows. So, you know that from the ideal gas law, uh, P sub I is equal to N sub I RT, where N sub I is the number of moles of gas I, Pi is the partial pressure, and so that means that basically N sub I over V, which is the concentration of the gas, right, is equal to Pi over RT. So the partial pressure is directly proportional to the concentration of the gas, right? You simply have to divide by RT and you convert the partial pressure into moles per liter or whatever the appropriate units might be in for the case at hand. So essentially, we have the partial pressure of the gas in the bulk phase, which we denoted pi a, which goes down only in the thin boundary layer to the value pi ai, which is its concentration at the interface. And then at the interface, the two concentrations are in equilibrium. Pi ai is in equilibrium with cai. And then once again, there is a drop from cai to the bulk phase concentration ca in the bulk phase, where A could be any gas. It could be sparingly soluble or highly soluble. Sparingly soluble being, for instance, oxygen. Highly soluble, um, the book actually that I have used refers to ammonia, but I suspect even carbon dioxide will fall into the same category. So, after going through this entire derivation, we basically arrived at this formula. Um, what we found was that uh, J, the flux, right, is essentially equal to an overall liquid phase mass transfer coefficient multiplied by Ca star minus Ca, where Ca star was what I said, a hypothetical liquid phase concentration. Um, in other words, it is that concentration of the liquid phase that would be in equilibrium with the given concentration, bulk concentration, pi A in the gas phase, right? So this is, at least in general, a hypothetical concentration because it's not clear where this concentration Ca star would actually appear in the concentration profile. But later on, when we went on and considered the case of insoluble gases, right, such as oxygen, we basically found that this is the picture that emerges. Basically, what we are saying is that if the gas is insoluble, there's virtually no decline of the concentration in the gas phase. So basically, in the gas phase, the decline, the expected decline, which we had in our earlier picture, which I'm showing with a kind of a red line over here, that picture never happens. In fact, there's hardly any decline and the line is virtually flat. So pi AI is essentially equal to pi A in the special case where the gas is insoluble, because the only decline that occurs on in the film that is in the liquid side. There is no change in the concentration on the gas side. Now, if pi AI is equal to pi A, then CAI, right, which by definition was, if you remember, CAI and HAI were related. We had HA to be equal to basically pi AI divided by CAI. I mean, because at the interface, the two concentrations are in equilibrium. Well, if that is the case, and if pi AI is equal to pi A, then clearly CAI is nothing but pi A divided by HA, right? And this is nothing but, this is actually a real concentration. This is actually approximately equal to Ca star. So in other words, because there is no decline in the film on the gas side, you actually have a real concentration pi A, right, which is the partial pressure at the interface, partial pressure of A at the interface, and CAI is exactly Ca star, right? So in the case of oxygen, which is sparingly soluble, CO star will be a real concentration. It will be that concentration that is in equilibrium with the partial pressure pi O in the bulk of the gas phase, right? So basically, ultimately, all you are saying is that the decline, and no, the ultimate expression that we got was essentially KL multiplied by, this is the expression we got finally, this expression over here. So what is clear is basically everything is being driven by this decline. That's it. Ca star minus Ca. So essentially the flux is driven by the concentration gradient from the interface to the bulk, where the concentration at the interface is essentially equal to that concentration in the liquid phase, which would be in equilibrium with the concentration pi A in the gas phase. That part clear? So this is just a quick review, and I'll let you revisit the case of highly soluble gas on your own. It's just the opposite, the converse of that. So then I kind of went on to say that this is not the only. As a matter of fact, um, there is a in sort of, I would say, more advanced studies, but there is a better model for it, even though the film theory is the most commonly used model. And the only reason why I mention it is that notice that we the expression, J equals KL multiplied by CA star minus CA, where KL, you go back and revisit the notes, is nothing but the diffusion coefficient of A in the liquid phase divided by LL, which is the thickness of the film in the liquid side. So this is the diffusion coefficient. This is the diffusion coefficient. And this is the film thickness. the thickness of the film on the liquid side. And the reason why I mentioned this thing in chapter 18 of BSL is that this is the penetration theory, which is more accurate. Basically, what it says is that you have gas on this side and you have liquid, thin liquid film on this side. But the important point is that it only looks at what happens during short contact times, whereas the film theory assumes that there is a contact for a long time, and therefore there is a steady state profile that is reached in the. So maybe I can just show it. So this picture over here in white, these arrows, they show you the velocity distribution. So this is the velocity distribution. This is how the velocity changes with distance from the interface. This is the velocity of liquid, right? The velocity profile of the liquid, right? As you move away from, this is the interface, of course. This is the interface. Now, imagine that the liquid sort of, this is actually the original picture we had. Oh, I should draw it here again. So the original picture actually we have is here is a bubble and the liquid is kind of flowing along it like that. And this is meant to take, an approximation to that kind of a picture. Imagine this liquid moving like this with the velocity profile shown over there. Now, if we look at the concentration profile of oxygen or the gas, in this case, I just call, let's say, gas A, we can imagine that at the boundary, the concentration profile will be at equilibrium, Ca star, right? And then, so I start here, this is distance. And let's say this is the concentration profile. Initially right over here, it may be like this. And then as it goes down, right, this place, the concentration profile will spread outward. So if this is, let's say, the x-axis, then as the liquid is flowing downward, the oxygen or the gas A will permeate further and further in the x direction, and ultimately stabilize at very long lengths. The film theory assumes that we are looking at the picture after the concentration profile has stabilized after long propagation in the z direction. Whereas the penetration theory says that there is only a short contact, and therefore the contact time becomes an important variable. And the important difference is that in the penetration theory, you get a dependence not on the diffusion coefficient, but on the square root of the diffusion coefficient. Okay, and that, it turns out, plays an important role in some aspects. So we don't have the time to cover it this semester because I think we have fewer lectures than a normal semester. But this is just for your information that there is an alternative theory called the penetration theory, which is actually more accurate, simply because the contact between the liquid and the gas is actually transient, as opposed to so long that steady state is reached. Okay, so with that sort of background, I think I can now move on. So the main formula that you have to remember that we have picked up so far is this formula over here that we will use over and over again. This one, J equals KL CA star minus CA. And then what I did mention later on, which I will flesh out a little more right now, is that J has units of flux, which is moles of gas A transferred per unit interfacial area, per unit time, and actually it needs to be multiplied by this quantity called the interfacial area per unit volume, which is often volume of the liquid, often denoted A. This is A centimeter square of interfacial area per centimeter cube of the liquid. Notice it is liquid, not liquid plus gas. So it is not the volume of the full dispersion consisting of gas and liquid. It is the volume of the liquid only. And this is for reasons that I will get to later on when we finally derive the mass balances as to why we choose the volume of the liquid and not the volume of the dispersion. So ultimately, we will be dealing with, we'll be multiplying this whole thing by A, which will give us KLA. And actually, typically, KLA is treated as a single quantity because it's very difficult to measure either KL or A separately. The experimental tools that we have allow us to measure only this thing jointly. I mean, we are unable to, not unable, but it's extremely tedious to disentangle KL and A separately, even though physically they're separate quantities. KL is a measure of the speed with which transfer takes place, and A is a measure of um, the interfacial area. These are two different physical entities, and they appear as a product, but it's very difficult to disentangle them experimentally. And so we typically just try to estimate KL times A, and it is often referred to in one breath as KLA. But keep in mind that these are two separate quantities. Okay, so I think that was a rather long review of the last lecture, but I thought it was worth doing it because I think we're moving at a relatively fast clip. So in today's lecture, um, um, okay, so in today's lecture, maybe um, thinking about what is the best way to proceed. So actually, um, the truth of the matter is that this quantity KLA is generally estimated um, by experimental techniques, at least two of which you will be looking at in your labs. Um, it is an extremely important quantity because, as I told you, um, in all aerobic fermentations, the quantity that most limits uh, the performance of the reactor is the availability of oxygen. And later on, we'll be doing a numerical problem that actually allows you to estimate what is the maximum amount of biomass you can get, given the limited speed with which oxygen can be transferred into a culture. Uh, but I still want to give you a sense of, um, you know, the theoretical estimation of KLA. And that means that I still would like to sort of spend a little bit of time. But before I go there, let's talk a little bit about this quantity CO star, so that you're totally familiar with it. Um, CO star, which is called, the word used for it is saturation concentration. So now we're talking about the the this CO star. Keep in mind, CO star was equal to essentially H for oxygen, which I call HO, say, divided by pi O, where pi O is the partial pressure in the Sorry, I'm writing it the other way down. Let me correct myself. This is pi O divided by HO. So going back to the picture that I gave you for Henry's law, we had CO over here and pi O over here. This is pi O equals H O multiplied by CO. So this is the relationship between the equilibrium concentrations, and maybe I should just, in this notation, this is the way I would write it. So the moment I give you any particular partial pressure, you can estimate the corresponding value. So pi O, this is in atmospheres, but easily converted to concentration in moles per liter if you multiply it by 1 over RT. And this is in often expressed in millimoles per liter, right? And as I mentioned to you, if you take, I've already given you this number, when pi O, when you take air, right? When you take air at 1 atmospheric pressure and the normal temperature 25 degrees C or 30 degrees C. So this, if this is, then the partial pressure in that case would be 0.21, because 21% of air is oxygen, and that gives you approximately 0.25 millimoles of liter, which I showed to you. This corresponds to about 8 milligrams per liter. That is the picture we have. When we see what happens with air. Now, it should be pretty obvious from this formula here, right? I mean, you can see right away that if I have, so let me just repeat it, if CO star equals the partial pressure of oxygen divided by HO, but of course, the partial pressure of oxygen is nothing but the mole fraction of oxygen multiplied by the total pressure, P total. So it becomes very clear that there are two ways of increasing CO star. If you want to increase CO star, and why is this question important? If you want to pump more oxygen, it's clear that you have to increase CO star. Well, one way to increase CO star is to simply increase the total pressure. Because if you increase the total pressure, then clearly the partial pressure goes up. If the partial pressure goes up, you will have more oxygen at the interface, right? That's one way of going about it. So it's pretty clear that CO star, and hence the oxygen transfer rate can be improved by enhancing the total pressure. The total pressure. As attractive as this idea is, it is not used very much in practice. I suspect because of the costs associated with it, right? The moment you go to high pressure, you need to have much more expensive material, and probably process costs also go up quite a bit. The second point, so this is actually the first point, right? This is the dependence on total pressure. The second point about CO star is that actually going back to again, maybe I should call this A, and let's call this relationship 1. Now, the other thing I'd like to point out is that in this graph is obtained if you have fixed temperature and liquid composition. In other words, if I were to increase the temperature, for example, right? If I were to increase the temperature, then I expect the volatility of the gas to go up, and therefore the graph would shift upward, right? Because for the same partial pressure, then I would get a much lower concentration in the liquid phase. Yeah, the gas will tend to live more comfortably in the gas phase as the temperature goes up. So this HO, it clearly depends on temperature, and as it turns out, it also depends on composition of liquid. So if I do the experiment with pure water, double distilled water, then I might get the white line. But if I start adding salts to the liquid, then its tendency to attract oxygen goes down, and once again the curve shifts upward. So this mathematically, what this means is, let me just summarize it. The dependence on the pressure is really straightforward, right? It's just increase the pressure and CO star goes up. Its dependence on the temperature and its dependence on the medium composition is embedded here in the variation of the Henry's law constant with the temperature and the pressure. And you can see these in table. So this I will simply summarize by saying, so A deals with uh, A deals with dependence on total pressure. B deals with dependence of CO star on temperature, but this happens through the variation of HO, the Henry's law constant with temperature. And you can see table, this is table 10.2 of Doran, right? Which shows that, for example, uh, it shows that CO star is equal to at let's say 0 degrees C is 15 milligrams per liter, but CO star at 35 degrees Celsius decreases to 7.5 milligrams per liter. Okay, so when I put air in contact with pure water, this is milli-Q water, so we're looking at the dependence on temperature. If I do the experiment at 0 degrees C and I do the experiment at 35 degrees C, I will find that the concentration of oxygen in the pure water that is in contact with the air, it will tend to hold more oxygen at a low temperature than at a high temperature. So at 35 degrees C, which is what we see in India, the solubility of oxygen has declined by almost 50%. Okay. They also give a formula somewhere. There's also a formula given. They say that this is a good representation. You have to take a look at. Actually, I should just show you the book rather than Oh, wait a second. So, here it is. So what I'm covering right now is hmm, yeah, there it is. So here it is. I'm covering this section right now. Estimating oxygen solubility, right? So ultimately, what we're looking at is the solubility of oxygen. When you take air and put it in contact with water, how much oxygen will you find in the water, right? So this is the point I just made. Oxygen solubility is directly proportional to total gas pressure and the mole fraction of oxygen in the gas phase, right? So this is proportional to YO multiplied by P total, right? Then the effect of temperature, which I just said is indicated in table 10.2, right? You can see that as the temperature changes, right, they are indicating higher and higher values of the Henry's law constant, which is exactly what I told you in my notes, right? I said that the increase of the temperature is tantamount to a shift in the slope of the graph that is relating the partial pressure to the concentration in the liquid phase. Um, and they also say that this data, right, which is actually for pure water. This is for water lacking any salts. For pure water, uh, this entire data has been fitted to equation 1048. Is 1048 visible to you? Is my screen
Yes, sir.
visible?
Yes, sir.
Uh-huh. So they've just fitted it. So this is giving you a sense of how the solubility of oxygen uh, in the presence of air changes with temperature. So you can either report it as oxygen solubility, or you can change the Henry law constant. This is like, it's just same thing really. It really doesn't matter. And finally, the second thing I mentioned was that this CO star also changes with um, it also changes with the composition of the liquid, right? So if I have salts, it turns out that uh, the solubility of oxygen, so it says here the solubility of oxygen is reduced by the addition of ions and sugars that are normally required in fermentation media. And somebody has estimated an empirical correlation right here. This is the empirical correlation. So I should simply mention that for the non, this is for the non-ionic parts of the medium, and this is for the ionic parts of the medium, and this is I forget what this is. This quantity is what is called ionic strength. I don't know if you're familiar with it. Have you heard of this quantity called ionic strength?
No, sir.
Oh, so this is basically Zi is the valence of the ionic quantity. Say, for example, Ca2 plus would have Zi equal to 2, and Ci would be the concentration of that quantity. So this quantity appears actually quite often in ionic systems because it is strongly correlated to deviation. High ionic strength systems start to deviate from what is called ideal solution behavior. Um, maybe we don't want to go there, but anyway, the bottom line is that as you add um, stuff to the medium, different kinds of salts, the solubility typically goes down. And this is shown in tables 10.3 and 10.4. So that should get you familiar with the fact that this CO star, which is nothing but, in our case, since we are dealing with a sparingly soluble gas, CO star is essentially that concentration. It was originally defined as that concentration, which would be in equilibrium with the bulk concentration pi A in the gas phase. But because our gas is sparingly soluble, it is also equal to the concentration at the interface. So it's easy to visualize what's happening here. CO star is the concentration at the interface, and the difference between CO star and the bulk concentration CO is what is driving it. And CO star depends on the total pressure in a very simple way. It depends on the temperature in a slightly more complicated way, because actually this dependence again, it comes quite straightforwardly from thermodynamics, but it has been removed from your curriculum. So it has a slightly more complicated dependence on the temperature, and a totally empirical dependence on the composition of the salts in the medium. So very often this is also a quantity that needs to be measured, although I must confess that in the experimental literature, they do a rather poor job of it. People just assume it to be 0.25 moles per liter and move on, because the effort probably required to measure it is a bit much. So I think that should cover the CO star. Now I'd like to move on to so let's see. C was dependence on composition, liquid composition, and again urge you to see Doran. Right, I pointed out the material to you. Now I want to spend a few minutes explaining the theory behind this quantity, the interfacial area quantity, which we call A. So this is the interfacial area. I should correct myself. This is not right. This is interfacial area per unit volume of liquid. This is the quantity which I have repeatedly referred to as A, which comes in the KLA. And I want to see if I can cover this in a really simple way. The first thing I want to show is that this quantity A, which is defined as interfacial area, so it is defined as interfacial area per unit volume of liquid, right? I want to show that this is equal to 6 divided by dB, where B is average bubble diameter, multiplied by epsilon over 1 minus epsilon. So keep in mind this dB is bubble diameter, so you have a gas suspension, and this quantity epsilon is what is called gas holdup, which is actually equal to, if you take a look at your vessel through which gas is being bubbled, then this is the total volume of the gas divided by the total volume of the gas plus liquid. So it's basically what fraction of the total volume in your reactor is taken up by the gas, right? Because the liquid phase is filled up with these bubbles, yeah. And I want to see if I can uh, somehow get to this. So let's see. I want to do. So we'll assume that for simplicity, this can be made more precise, but I want to cover this in like 5-10 minutes. So I'm going to make some simplifications. I'm going to assume that all the bubbles are of the same size, dB. Although the reality is that the bubbles have an entire distribution of sizes, but uh, you know the argument easily goes over. All you'll have to use is some sort of a mean diameter. It's actually called the mean Sauter diameter. But let's just make the simple assumption that all bubbles have the same diameter, dB, and the gas holdup, which is defined as, which will be defined as the volume of gas uh, divided by what fraction of the total volume is occupied by the gas. This is a quantity known as gas holdup. And the reason why I'm putting this before you, I'll derive this equation, is that ultimately it turns out that the bubble diameter is a quantity that you can play around with by changing the power input to the impellers. And therefore, you can play around with A, you can change A basically by changing the power that you deliver to the impellers. That's what will come out. And so this will give you some sort of an estimate, some way of estimating this quantity KLA. That's finally what will come out of it. So just to explain this to you, which is, I hope, going to come through. I'm really cutting down 2 pages to basically 3 lines. A is defined as the interfacial area divided by the volume of the liquid. Okay. Now, I can write this as equal to, this is of course equal to um, interfacial area, right? This is the interfacial area, right? Uh, per, not per unit volume of liquid, but per unit volume of the total dispersion. When I say dispersion, I mean liquid plus gas, right? Taken together, divided by volume of liquid divided by volume of dispersion. So I've just divided both numerator and denominator by the volume of the dispersion. Okay. Now, the numerator, which is interface. So first of all, notice that the denominator, which is the volume of the liquid per unit volume of the dispersion, this is nothing but by definition 1 minus epsilon. Is that part clear? Am I making sense? Maybe I'm just going on and on. Can people follow what I just said?
So could you explain the last part again?
Actually, I'd like you guys to simply interrupt me if you don't follow what I'm saying. Is that okay? I mean,
Yes, sir.
huh. So I'm saying that by the definition of A is interfacial area, that is to say, the area of the gas liquid interface per unit volume of the liquid only. Even though I have a gas dispersion where there's liquid and gas, I am basing the interfacial area only on the volume of the liquid. The reason for this will become clear when we take the mass balance ultimately, because this is sort of forced on us. Now, if I define it in this way and I divide both the numerator and the denominator by the volume of the dispersion, that is to say, the volume of the liquid plus the volume of the gas. So this denominator is the volume of the dispersion. It is VL plus VG, total volume of the dispersion. then you can see that since epsilon is defined as Vg over Vg plus VL, this quantity is nothing but VL divided by Vg plus VL, because it is the
Yes, sir, it
volume.
makes sense.
So now, if Vg over Vg plus VL is epsilon, then VL over Vg plus VL is 1 minus epsilon. So basically what I get is that A is equal to 1 over 1 minus epsilon, right, multiplied by interfacial area, right, per volume of dispersion. Okay. Now, I'll simplify this a little bit further. So I will write this as 1 over 1 minus epsilon, and this I will write as interfacial area, right? So this is interfacial area. That means this is the area of the surface of the bubbles, right, divided by the volume of bubbles multiplied by volume of bubbles divided by volume of dispersion. So this is just rewriting. I've rewritten this thing by dividing both the, I've divided the volume of bubbles on both sides. Right? This is not legible. Let me rewrite it. This is volume of bubbles. So this is interfacial area, or if you don't like the word bubbles, you can write this as gas phase, and this as gas phase. Now, what is this quantity over here? Volume of gas phase per unit volume of dispersion.
So epsilon.
So this is epsilon. Now let's take a look at the quantity on the left. On the left, the interfacial area per unit volume of the gas phase is nothing but, I can rewrite this. This is nothing but, if you think about it, this is nothing but surface area of bubbles divided by volume of bubbles. Would you agree with me?
Yes, sir.
So what is this ratio? If I assume that all bubbles have the same size dB,
Yes, sir. So it should be 6 by the
basically
diameter, 3 by the
if I
radius.
assume all bubbles have the same size, then the surface area is what? 4 multiplied by pi r squared. So, I mean, that is, I think, pi over 6, is it?
6 by D, sir. 6 by D.
Ah,
Yes.
so that is,
So it will come out to be 6 by D or 3 by R.
so this is 6 by dB. So there you go. You end up with 6. So here you have 1 minus epsilon, here you have epsilon, here you have 6 over dB. So you end up with 6 over dB multiplied by epsilon over 1 minus epsilon. So that's exactly what we set, that's exactly what we set out to show. So this is A equals 6 over dB multiplied by epsilon over 1 minus epsilon. And it turns out, now I'll just simply tell you, this I have to skip because this is a bit kind of, now what determines the diameter of the bubbles? Well, what determines the diameter of the bubbles is a constant tussle between the inertial stresses produced by massive turbulence that are tending to break the bubbles and the surface tension forces which form like a skin around the bubble that prevent it from breaking. So basically breakage will take place bubbles will break essentially when these two forces become comparable, and they will be stable if the surface tension forces are much bigger than the inertial forces. So when you apply this kind of argument, basically you start taking orders of magnitude of forces. It turns out this is from, I would use the word semi-empirical theory. From semi-empirical theory, this is actually not that easy to understand. It is based on what is called Kolmogorov theory of turbulence. Theory of turbulence, which is kind of a little hard to understand, frankly, even for me. dB turns out to be, it turns out the theory shows that it is proportional to the surface tension is sigma. It is proportional to, this is 3 over 5 divided by rho L, which is the density of the liquid, to the power 1 over 5. And this is the quantity we know from our earlier discussion in the last chapter, VL to the power 2 over 3. And actually, experiments show that the data is well fitted by the constant 0.7. So this is the surface tension. And this is liquid density. And this is power draw per unit volume. And so you can see that the higher the power draw, that means the more power you pump with your impellers, the smaller will be the bubble diameter. The smaller the bubble diameter, the more the uh, interfacial area. Now, I should also point out that this same, let's now apply, we have only looked at the effect of PG over VL on A, but it is also worth considering what would be the effect of PG over VL on the mass transfer coefficient, KL. Now, if you increase PG over VL, keep in mind, let's work our way through this, assuming the film theory, which means that KL is essentially DL divided by LL, which is the thickness of the quiescent layer on the liquid side. Would anybody like to take a shot at what the effect of increasing power draw per unit volume would be on KL? So it's clear that it's increasing A, right? What would be its effect on KL? KL we know to be diffusion coefficient divided by LL. So I've given you, there are only two quantities. If I stir it more vigorously, can anybody take a guess? I mean, at least allow your mind to wander. No. Diffusion coefficient will change if I change the power draw per unit volume. Actually, am I audible?
Yes, sir, you are.
Uh-huh. Do you think the diffusion coefficient will change? Okay, so I think it's probably not covered, but so basically the bottom line is that if you go back to your film theory model, we assume that this had a thickness LL and this had a thickness LG. The diffusion coefficient here is DL, the diffusion coefficient here is DG, and K's were, this is KG and this is KL. This is the picture we had. Well, these DL and DG are diffusivities. These are physical quantities. Yeah, they're not affected by agitation significantly. I mean, DG and DL are by definition quantities that are measured in the absence of convection, right? I mean, these are by definition, right? Diffusivity is what measures mass transfer when you have no convection at all. And so if you start creating more convection by for instance, pumping more power with your impeller, that doesn't change the fact that DL and DG will be measured in the absence in any case. But these boundary layers, they tend to shrink depending on the agitation. The more you agitate, the lower the thickness of the boundary. So if you're agitating the liquid massively, LL will go down, and that is how one rationalizes the increase in KLA. So coming back to what I showed you over here, the increase in the power per unit volume. So increasing PG over VL decreases the bubble diameter, which implies that A, which is inversely proportional, Ka increases. Also, it turns out that Pg over VL increases. So I should actually write it in this way. When this so briefly, Pg over VL increases implies that dB decreases, which implies that A increases. Also, when PG over VL increases, then LL decreases, which implies that KL increases. So PG over VL, the power draw per unit volume, tends to pump up this KL is quantity KLA, each of them individually. It's also worth mentioning that the surface tension has a stabilizing role. Now, they say that when you add, say for example, I don't know, in reactors, people often add this thing called anti-foam. This is a kind of a surface active agent, which is added to prevent the foam from forming at the top of the reactor, which then actually tends to increase sigma. And because it increases sigma, the bubble diameter increases, and therefore the mass transfer coefficient goes down, A goes down. So on the other hand, for example, anti-foam, which increases sigma, which increases sigma, tends to decrease A and hence KLA. Okay, so I think that's basically given you a very, very brief overview of what is KL and what is A, right? I mean, this is like and now we get to the heart of the problem, which is the development of mass balance, right? For oxygen in, now it'll turn out that we have two different balances in liquid, one in for the gas oxygen that is in the liquid phase, and one for the mass balance that is in the gas phase. So there are two different. So what are we getting at here? See, in the very first few lectures, we talked about differential equations describing, you know, what is happening to the substrate, product. Here's an example, right? I mean, I'll put it on the side. You remember we derived, for example, for a chemostat, that ds dt equals dsf minus s minus rs times x. We derived a similar differential equation for biomass, for product. But notice that we never had a differential equation for oxygen or carbon dioxide. I mean, there's nothing for gases. And the reason was that we were not ready for it. And why were we not ready for it? We were not ready for it because we did not know how to describe how oxygen is getting pumped from the gas phase to the liquid phase. We just had no idea. Well, now we have a model for the rate at which oxygen goes from the gas phase to the liquid phase. And since we have that model, we can now proceed to do so. So first, so this is basically, it will also explain to you why we define A as the interfacial area per unit volume of the liquid. So let's do this for a continuous reactor, and it can easily be specialized for, this is your impeller, and let's say this is your sparger. Okay. Now the notation that I will use is, this is the liquid flow rate F, and the gas flow rate I will assume Fg, and I will use Fg in and Fg out. The reason why I have different notations for in and out is that there is no guarantee that the gas flow rate in is equal to the gas flow rate out. Well, the reason is that the cells that are living inside the reactor frequently produce more carbon dioxide than they take up oxygen. In other words, the moles of CO2 produced can be 2, 3, 4 times the number of moles of oxygen they consume, especially if they are in the fermentative mode, right? And if they are operating in the aerobic mode, for every mole of oxygen consumed, they release 1 mole of carbon dioxide. So gas in is equal to gas out. But if they start producing more carbon dioxide than they consume oxygen, then Fg out can be bigger than Fg in. That's not the case for the liquid phase. I mean, for the liquid phase, you can be sure that there's hardly any change in the flow rate. And the reason for that is there is literally no change in the density going in and going out. I mean, the density of the liquid, the pure liquid, we have basically medium going in, it has no cells in it, is around 1.02, 1 point something like that, because of the salts that you've added to the medium. And its density going out is basically maybe 1.08, because the cells also have a density which is very close to that of pure water. So because the density going in and out are equal, then that means the flow rates going in and out are also equal. So here we assume flow rate in is equal to flow rate out. But for the gas, we do not assume that the flow rate in is equal to the flow rate out. Okay? Now, it turns out that at least in small scale reactors, um, you see, actually, um, if you take a bubble over here, right? So we know now, so we know that, let's say this is a bubble here. Now we know that these bubbles are getting somewhat depleted in oxygen. That has to be the case, right? I mean, um, the composition of the bubbles inside the reactor has to be lower than the composition. So if the concentration over here, let's say of oxygen, I say is CO in, then so first assumption that I will make is that bubbles are well mixed. So that means that these bubbles, they are thrashed around so well, right? And this is experimentally tested, at least in lab scale reactors. Not true for large scale reactors, but certainly in small lab scale reactors, that you're randomly throwing the bubbles all over the place. So all bubbles have the same composition. Is that part clear?
Yes, sir.
And the second thing is, this assumption is very similar to the one we make in liquids. When we say that the liquid is well mixed, what we mean is that the concentration S, say for example, of the substrate or the product that you observe in the exit stream, is equal to the concentration S or P in the liquid inside the reactor. I mean, that is the meaning of well mixed. Well mixed means two things. One, the composition does not change with space inside the reactor, right? So the liquid concentration is the same no matter where you go inside the reactor. And the second assumption is that what comes out is essentially identical to the space independent concentration inside the reactor. Those are the two attributes of the well mixed assumption. Well, I'm making the same assumption about the bubbles. So, what that means is that the effluent concentration here, right, is no different from the composition of the gas inside the bubbles. You following? I mean, the bubbles are all have the same composition, which is lower than the concentration CO out. So inside these bubbles, so I have the concentration, let's say CO out here. This is the same as the concentration CO out inside the bubbles. This CO out is actually less than CO in, which is the oxygen. So it's as if oxygen, the air came in and instantly it basically, the concentration drops. Not unlike what is happening in the liquid phase, where it comes in at a feed concentration SF and instantly drops to S upon encountering the feed. So it may sound a little bit unintuitive, but can you see the analogy between the two? In the case of the liquid, the feed comes in at concentration SF of, let's say, glucose and instantly drops inside the reactor to S. Likewise, the gas comes in carrying CO in millimoles per liter of oxygen, and instantly the bubbles inside have this depleted concentration CO out. Is that making sense? Under the well
Yes,
mixed
sir.
assumption?
Yes, sir, it is.
Uh-huh. So now, with that assumption, you can now start to build uh, your your mass balance equations. Okay. So what would my so this which implies which implies that the bubbles and headspace have the same concentration CO out, which is less than, somewhat less than CO in. Okay. So now let's start to, this is my assumption. Okay. Now let's start to build our mass balance. Um, so under many conditions, actually, second assumption is actually if you we're going to run out of time, but so when you see so under many conditions, especially under aerobic growth. So this is second assumption. So under aerobic growth conditions, I should say CO out is certainly less than, is certainly less than, but it is close to CON. I mean, the two are not terribly different. There's only a small decrease in the level that you observe. Um, I'm trying to see if I should just postpone this to the next one, or so actually, tell you what, I think we'll just call it. We have only 4 minutes. This is far too important, so we'll close it in the next lecture. I think there's no point in trying to push it for 4 minutes. So I think we'll call it a day, and we'll close this on. I hope we can finish this by Thursday. So that leaves us with how many more lectures? I think 4 more.
Yes, sir. Around about.
Okay, and that's, I think, good enough to. So I think we've covered less than what is typically covered, but I'm told that this is a shorter semester. Is that correct? I mean, I think 6 or 7 fewer lectures.
Yes, sir. I guess it's 12 weeks instead of 14 weeks.
So, I mean, there is stuff that I cannot cover, but that's okay. I mean, this is an undergraduate course. It doesn't really matter. So, I also will suggest that you solve some problems from the previous stuff that we did, mixing. These are problems at the back of Duran. You know, I can suggest problems for you to do, but you know better than I do. The solutions are available on the web, so you can actually read up the solutions too. You're also welcome to work together to do it. I mean, that in fact is a better way, because when you talk to each other, maybe some new thoughts will come to your mind. But my suggestion is that, if you work in groups, you can actually pretty much do the entire set of problems. I mean, even if I recommend 10 out of the 25 problems, you could you're a class of 50, between 50 of you in groups, it shouldn't be that hard to just nail all the problems. I mean, I'll give you a set of about 10, 12, but my suggestion is just do all of them. Because once again, you'll be probed on your ability to explain what you did to me. So uh, the the problems basically, I think I just want to say, in mixing, what we did was we considered the things independently, right? We did gas mixing, and then we did liquid mixing, and then we did solid mixing. Whereas the problems kind of mix and match. There are problems in which both things are happening. Now tell me what I should do, or all three things are happening. So, am I correct? I mean, there is really no need to be bashful. The solutions are all available to you, right? They're available on these websites. I mean, you can just download the solutions to the problems. Is that right or wrong?
So it's probable. Like I haven't checked yet, but it's like possible that they are.
It's all over the internet. It's not an issue, and I have no problem with that. But the point is that you don't just these are not problems requiring no thought. Uh, it's not कि यार, it's not one of those s is equal to half at squared. A दे दिया t दे दिया s निकाल दो, right? I mean, at the end of the day, are you using your head? What are you really doing? That's the kind of thing that I'm looking for. So the solutions are there. Reflect on the problems. That's all I'm saying. And the solutions are all there. So I will not go terribly outside uh, what is there in chapter 8 and the problems given therein. My suggestion is you start trying them out. It can't be that hard. You still have well over 2 weeks, and between the 55 of you, or whatever the proportion that is actually interested in doing anything, you can work them out. Okay, is that okay?
Yes, sir.
Yes, sir.
So one more thing. So could we have another doubt session in the end, like at the end of things, so that we can like
So I have
probably discuss the problems.
so I will maybe hold not one but maybe two. I've missed two lectures, so I will make up at least one of those lectures by having a makeup session. Right, I missed two lectures. I think one was immediately after I held the Viva, and one may have been immediately before the Viva. So I will hold a makeup session, but that'll be off of the lecture. You get what I'm saying? I mean, it will not be uh, during the normal lectures. You will have to schedule a separate session because I can't afford to lose any more lectures. I mean, it's going to
Fine,
be
sir.
pretty fast. It'll going to be, from now I'm going to zip. I have one more topic to cover. Heater I'm skipping completely. I will not even touch it according to the syllabus. There is a last topic on, I believe, consistency of data using elemental balances. I don't think there's any time to do that. So basically, I will cover next other forms of reactors, fed batch, recycle, uh, possibly um, reactors in series or parallel, and that's about it. So you have to do the problems from chapter 8, from chapter 10, and when we come to the last part, which is reactors, I'll be giving you more problems that I have collected, similar to the tube sheets that I gave. You're expected once again to understand the problems, and so may I just point out that I also had a number of people last time on the minors. I have done the problem, but I have not calculated them. Which is, I mean, like, it's just, I mean, the whole trick was, noticing something when you calculate. So approximately 70% of the class were totally clueless, right? I mean, there were tricks on the problems that people didn't even pick up. Uh, there's no point in मैंने किया हुआ है, and they show me some one line that I wrote down the formula you gave. So think of this problem as a course in which the problems are not like I mean, so this is like the JEE, right? I'm not expecting you to do some dumbass, calculation of putting two values and ab to kar lunga, yeah. This is the formula. I have not done it. The point was that when you do the calculation, you see something wrong. So please don't do the problems by saying, I have done it and I know I can do it. Because, then when you ask, and I ask questions, I hear these absolutely superficial answers that are worth nothing, right? I mean, some of them were just repeating the formulas I gave in class, which is just, I mean, if that's what I wanted from you, I wouldn't do a 15-minute Viva. You understand my point? So take that the way you want to. I've made my intention clear now. If you're solving the problems and I'm asking you about those problems, I'm clearly not asking you which formula you used. I'm going to ask you deeper questions about what are you doing. So give some thought to what you're doing. Is that part clear?
Yes, sir, it is.
Okay, all right. So I'll see you on Thursday then.
Fine, sir. Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.